Chapter 5.2 is on classifying polynomials. A polynomial, we talked about this briefly in the last video. A polynomial is any expression or function where the variables, it's all about the variables, are not in radicals, they're not on the bottoms of fractions, and where the powers of the variables are whole numbers. So like if we look over here, whole number power, this has no power. So this is a polynomial. Whole number power. All of these things have whole number powers. Since they have whole number powers, it makes them polynomials. This one looks kind of weird because there's a root 5, there's a 1.24, there's a negative 1/2, and there's a 6.23. But all those things that I just boxed, all those weird numbers, are coefficients. And the coefficients don't actually matter, it's just the power on the variable. So everything over here isn't a polynomial because that x on the bottom of a fraction, or that x inside of a square root, or that x has a fraction power, or a decimal power, or a negative power. Any weird powers happening to a variable ruin the polynomialness of an expression. And that's not a bad thing. It's not like bad to not be a polynomial. We're just trying to classify things in certain ways. Two of the more important parts or components of polynomials are the degree and the leading coefficient. Degree means the highest power. So when you look at some polynomials, the degree is the highest power. Here, the degree is 2. Leading coefficient is the coefficient on the degree. So in this polynomial, the degree is 2, and the leading coefficient is this negative 2 right here. So over here, the degree is 5, and the leading coefficient is negative 12. The sign is really, really important, so hang on to the sign. Take a second and pause the video and find the degree and leading coefficient on the next 3 functions or expressions. I guess they're all functions. This one has a degree of 4 and a leading coefficient of 3. This one has a degree of 3 and a leading coefficient of 4. So both of these aren't in standard form. We would like to put this in standard form, so we'd make it 3x to the 4th plus 5x to the 3rd minus 12x squared. And this in standard form would be 4x to the 3rd minus 3x. This one looks like it has a degree of 12, but it actually doesn't because it's not a polynomial. And if something isn't a polynomial, it's not going to have a degree. The degree tells us special things, which is why that matters. So we now classify polynomials based on the degree they have and the number of terms that they have. If something has a degree of 0, that means it's called a constant function, like y equals 12. This is the same as y equals 12 times x to the 0. Having a degree of 0 means you have a constant function. Whatever x is, y doesn't change. Y is 12, y is 12, y is 12. If it's linear, that's a first degree function. We call those linears. Second degrees are quadratics. Third degrees are called cubics. And then the terms quartic and quintic we don't use very often. But quart means 4 and quint means 5. It's a fourth degree function, fifth degree function. And then over here is the number of terms. If you have one term, it's called a monomial. We did monomial division last lesson. 2 terms is a binomial, and then 3 terms is a trinomial. Mono, bi, and tri means 1, 2, and 3. So this would be called a linear monomial. This is a quadratic binomial, and this is a quadratic trinomial. So quadratic means biggest power is 2, trinomial means there's 3 terms. And these are just things that make it easier for us to communicate about what we're talking about, and to know how these functions are going to behave. Okay, so now the degree and leading coefficient are important because they tell us useful things. The first and maybe most important thing is the degree tells us how many roots there are. A 4th degree polynomial has 4 roots, real or imaginary, one or the other. So if I had like x to the 5th minus 3x squared, this is a quintic binomial, 5th degree power 2 terms. This would have 5 roots. They might all be real, there might be some real, some imaginary, but we know there's 5 solutions to a 5th degree polynomial. Secondly, the degree tells us how many potential terns there could be. And a word for term is often max or min, but sometimes you can have terns that aren't exactly maximums or minimums, and I'll explain that a little bit later on, although maxes and mins are examples of terns. So if we look at this graph over here, think about this graph like it's a map from above, and your car driving along this road. And as the car drives, well, here it has to turn to the right. You would twist the wheel to the right. That's your first turn. Then somewhere in here, you twist the wheel to the left. And then somewhere here, you twist the wheel to the right, and then left, and then right. This has 5 turns. 1, 2, 3, 4, 5. A 6th degree polynomial has 5 turns. So whatever the degree is, there's at most 1 less number of turns. So if I had a 7th degree polynomial, there could be at most 6 turns. But there could also be 4, and there could also be 2, and there could also be 0 that go down in even pairs. So it could be 6, 4, 2, or 0 turns. And I can't write the word turns. Whereas here, the 6th degree function can have 5 turns, or 3 turns, or 1. They decrease by even amounts, by 2s. But there's never more turns than the degree. It's always 1 less than the degree. Finally, the leading coefficient and the degree tell us about the end behavior of the polynomial. End behavior means which direction it points at the end. What happens as you get to very, very high x values or very, very negative high x values. So end behavior is what happens to a function as it goes really far towards the right at positive x and really far towards the left at negative x. We're trying to determine if the graph points up or down as it moves left or right. So there's these two components. And there's really 4 possibilities: up and left, down and left, up and right, down and right. And there's these 4 categories. It could be an even degree, like x to the 4th or x to the 12th, or an odd degree, like x to the 7th or x to the 1st. And you could have a positive leading coefficient or a negative leading coefficient. Even degreed functions always point the same direction. So an even degreed function will point up on both sides or point down on both sides. So an example is like this. If you have a positive leading coefficient, then as x goes to the left, the graph goes up, and as x goes to the right, the graph goes up. And we phrase it that exact way. As x approaches, this arrow means approaches, as x approaches negative infinity, f of x approaches infinity. This really means as the x value goes up, as the x value goes left, the y value goes up. And as x approaches infinity, as x goes to the right, the y value also goes up towards infinity. Because again, we're talking about this part here and this part here. So that's an even degreed positive leading coefficient polynomial. For example, this. That could maybe be the polynomial that gives us this graph. Notice how the y-intercept of that graph is 0, so I had to put a 0 there. If you have an even degree with a negative leading coefficient, the graph is going to do something like this. It points down on both sides. The key is even degrees point in the same direction. They either both point up or both point down. So here we would say as x goes to the left towards negative infinity, f of x goes down towards negative infinity. And as x goes to the right towards positive infinity, f of x is also going down towards negative infinity. As the graph moves this way, it goes down. If that little burp I just did appeared on the microphone, I apologize. But I'm not going to go back and edit it, so get over it. Maybe I'll burp again, because I've got that kind of power. Even degreed functions point the same direction. If the leading coefficient is positive, they go up. If it's negative, they go down. Odd degreed functions don't point the same direction. In fact, they'll always point in an opposite direction. They'll point up and then down, or they'll point down and then up. They point in opposite directions. If you have an odd degreed function with a positive leading coefficient, the side on the right goes up, so the side on the left goes down. I don't know what happens in between. Anything could happen in between, but on the right you go up, on the left you go down. So as x goes to infinity, f of x goes to negative infinity. Sorry, I keep writing these kind of half backwards, because I should be starting with a negative infinity here. As x goes to negative infinity, as it goes to the left, y is going down. And as x goes to the right, the y value goes up. And then the other one just switches. As x goes to the right, nope, I'll start with the left again. As x goes to negative infinity, f of x goes to infinity. And as x goes to infinity, f of x goes to negative infinity. And I know that my handwriting gets sloppier as I go. I apologize, but also get over it. Now this can feel like a lot to remember. There's 1, 2, 3, 4, 5, 6, 7, 8 different possibilities, and each of these bits have 2 pieces. So I just wrote x and f of x 16 times total. So if you're looking for the shortcuts or the ways to remember it, think of it this way. If you were to do f of a trillion, and now my pen is slowed down. If you were to do f of some really, really, really large number, if the first thing is positive, it's going to get really, really big and positive. And everything that comes after doesn't really matter, because the positive makes it just blow up and get really, really big. So if the leading coefficient is positive, both of these point up. It doesn't matter if the degree is even or odd. If it's positive, you know it's going to go up. But then think about doing f of negative something really, really big. Well, in an even function, the negatives cancel. You do a negative times itself, times itself, times itself, an even number of times, the negatives cancel. So that still goes up in the even one. But in the odd one, if I was to do like f of negative 1,000 or negative 1,000,000,000,000 or a negative really big number, but I was going to plug that into negative x to the third, let's say, this ends up being a negative number when I plug it in. X to the third is going to come out to a really, really, really big negative number. So if this was a positive leading coefficient, it points down still. However, if it was a negative leading coefficient, it would then pop back up. So if you ever aren't sure what the end behavior is, just plug in a really big positive number or a really big negative number and see what happens. If it's positive, it goes up. If it's negative, it goes down. I hope that helps, but just try to remember, even degree functions face the same direction. The positive leading coefficient affects the right side, always the right side. So if this is positive, the graph goes up on the right side. It doesn't matter if it's even or odd, the graph goes up. And if you still can't remember these things, think about basic functions. Okay, y equals x squared is a basic even function where it points up on both sides. So as x goes to infinity, f of x goes to infinity. Same with negative infinity. And I did this in the wrong order again, so I'm going to put a little negative here and a positive here. And if the leading coefficient is negative, y equals negative x squared, they both point down. So think about that for your even functions. Y equals x to the third is a really basic odd function. It goes generally like this. Although if you're just doing plain old x to the third, it actually graphs like this. This is y equals x to the third. Up on the right, down on the left, or you switch it if it's a negative leading coefficient. Okay, I think that's all we have for today. Nope, not at all. We actually have like 3 more examples. How long has it been? I don't know. I should probably edit this part out of the video because now it's like you're going to be checking the clock and trying to check out of this. But I probably won't. You'll probably hear all this. This is an even degreed function. It's going to point down on both sides. It also has a y-intercept at 8. I've not talked about that, but there'll be a y-intercept at 8. What else do I know? The number of roots. There's going to be 4 roots because that's the degree. Because the degree is 4, the leading coefficient is negative 5. So for the end behavior, as x goes to infinity, f of x will go to negative infinity. And as x goes to negative infinity, stop doing it backwards, Grant. Did I used to do it this way all the time or something? Why is that? Anyways, they're both going to point down. They both point down. The trickiest one here is the possible number of turns, I think. Since the degree is 4th, there's 3 possible turns or 1. It could be 3 or 1. So I'm going to make a graph that points down on both sides, has a y-intercept at 8, and has at most 3 turns. So I'll go 1, 2, 3. Beautiful. So this has 2, the graph that I just made up, which might not actually be this graph, it's just kind of a sketch, has 2 real roots and 2 imaginary roots. 2 roots here. Next, same problem, different thing, same thing. This is an odd degreed function with a 5th degree. The leading coefficient is 3. The y-intercept is again 8. Ooh, gosh, I'm crazy. The degree is 7. So the leading coefficient is negative 1. Because it's an odd function, they point in opposite directions. The leading coefficient is negative, so this one goes down and this one goes up. And there's going to be at most 6 turns. Now I don't have to graph 6 turns. If I wanted to, I could do this. 1, 2, 3, 4, 5, 6. And draw my graph like that. And then just call that point right there 8. And there's my y-intercept. There could also be 4 turns or 2 turns or no turns. Those are all possibilities. Just know there can't be 8 or more, 7 or more, and it's never going to be an odd number in that case. So I would say as x goes to infinity, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to infinity. But I don't want to write that one out. Finally, we'll do the opposite. Here's a graph. What's the sign of the leading coefficient? We know the leading coefficient is going to be positive because the right side is pointing up. The right side tells you the leading coefficient sign. The end behavior, these are both going up. So as x goes to negative infinity, f of x goes to infinity. And as x goes to infinity, f of x goes to infinity. How many turns are there? This one gets kind of weird because this counts as 2 turns. There's a turn, remember you're a car on the map, you're looking above at a car. You turn left here, there's 1. You turn right there, there's 2. You turn left again, there's 3. This has 3 turns, even though it only has 1 maximum or minimum. In this case, there's a minimum right down here at the bottom. So this has 3 turns. Since there's 3 turns, and how many roots do we have? We only see 2 real roots. We don't quite see the imaginary roots, but we know there's going to be a couple. I'll tell you how I know that in a second. Because there's 3 turns, the degree is at least 4. It's at least a 4th degree function, but it could be 6 or 8 or 10. And so I know there's got to be some imaginary roots, because if the degree is 4 and we only see 2 real roots, there must be 2 imaginary roots or more. And the y-intercept looks like it is 1. 1, 2, 3, 4, 5. Yes, the y-intercept is 1. Okay, I'm going to call that good. Thank you for watching. As my cosine wave goes up and down and back and forth, will you please consider liking, sharing, subscribing, telling your friends, everything. And if by chance you're a teacher who came across the video and liked to use the curriculum that I wrote to go along with it, you can find that at the website listed down below. At this point, I'm just going to start stalling so we can keep watching it go back and forth, because when it bounces, it really just sort of mesmerizes you. It kind of looks like a DNA helix, maybe, or perhaps this is... It doesn't quite look like somebody's blood pressure that you'd see on a monitor in a hospital. Oh, like one of those Chinese finger traps. Is that racist if I say that? I don't think so. I think they're called Chinese finger traps. They're pretty cool. You like put your fingers in and you try and pull them apart and they squeeze tighter, and you realize you have to push your fingers back together to get it to come out. And there's probably some metaphor in there for life or something. But no, I'm just watching this thing go.